Afternoon, everybody, and welcome to Flatland. It's good to see so many faces on the Zoom screen. Why are we having this workshop? I think most of us would agree that quantum field theory in 3 space-time dimensions, particularly quantum field theory involving relativistic fermions, is interesting. It has several distinctive features, and it's been I would say a theoretical playground for many, many years. But the whole field has been kind of dynamically refreshed more recently, I would say in the last 10 years, by the fantastic applications in condensed matter systems, with graphene, with topological insulators, with many other kind of layered systems. And so we felt it was kind of a good time to try to bring together people from different communities with perhaps traditionally different interests. So we've tried to bring together both people who've been working many different theoretical techniques, both analytical and numerical, and also people with more whose focus is more directly concerned with applications to condensed matter physics problems. Perhaps even problems in cold atom physics, who knows. The genesis for this meeting actually came about quite a long time ago. I think John Gracie and I were having a chat in my office, and we thought it would be nice to try to get something going. And we very quickly and fortunately managed to persuade Holger Gies and Igor Hubbard to join us. That was in the spring of 2019. And so we thought that Trento would be the ideal place to host such a meeting. We all have very positive experiences and impressions of coming here and talking and hearing new things. And we originally had a workshop scheduled for June of 2020 last year. And you can guess why that didn't take place. So we had to, I was going to say reluctantly, but we were really forced, as you can imagine, just to postpone. We received a lot of encouragement and advice and support. I'd particularly like to thank Joachim Vombach, who was director of ECT Star at the time. And kind of during the long night, the candle was kept burning by Lucas Janssen, who gave us a wonderful talk, both live, and now you can also view it on the ECT Star YouTube channel in October of that year. So I'm probably going to put the link to Lucas's talk in the chat, so you can go, after you've had a full day here, you can go back and celebrate by watching Lucas talk later. Anyway, what happened? We postponed the workshop for a year. Unfortunately, we still have to be online because travel restrictions and life restrictions are still with us. And here we are. I'd like to thank as well Het Arts, the current director of ECT Star, who I think is going to give a few words of welcome in a minute, for the support and the advice that he's given us in leading up to this. I'd also like to thank Susan Dreesen from the local ECT Star organization for just getting everything together and making it work. And Susan's here at the moment, and she's recording what's going on. So, as you guessed, the main medium for the workshop is going to be Zoom. We're going to have 4 Zoom talks per day, more or less, except for one day where we have shorter talks. And the kind of etiquette, I think, that we'd like to invite you to follow is fairly straightforward. When the speakers are giving their presentations, it's best if you're on mute, so that there are no extraneous sounds from family pets or other family members during the talk. And also to kind of save bandwidth, probably we should all turn our videos off during the talk. We've actually got 70 registered attendees at the workshop spread across many time zones. They won't all be here at once, but there will be quite a good number. In order to manage the question sessions, it would really be helpful to the session chair, that's going to be me today, if you can put questions in the chat in the first instance, and we will try and do our best to get around all the questions. It may well be that we're not successful, in which case you'll notice if you look in the timetable for each day, there's a long break scheduled each day for between 1 3/4 to 2 hours. And in that time, I invite you to come together in another software environment called GatherTown. There is a link to GatherTown in the chat already, which Susan has put up. And this is a little, if you've seen GatherTown before, you'll know how it works. If you've not seen it before, it's a bit of fun. It's a little bit like a 1990s video game. You can create a little avatar and walk around a beautiful virtual meeting environment. There are gardens, there are fountains, there are coffee machines, and there's a big room full of posters. So we actually have quite a few poster contributions to the workshop, which have all been uploaded or in the process of being uploaded. There is a formal poster session scheduled for Wednesday, but I'd encourage you to go and have a look even before and certainly afterwards. And just if you're interested in a poster, why don't you send a chat message to its author? If you've made a poster, if you've contributed a poster and you particularly want somebody here to come and look at it and discuss it with you, why don't you send a chat message to them? Don't be backward. The whole point about this informal session is to try to recreate what's so precious about meeting together at any point at any time, but particularly I think in Trento, it's the walk in the garden with the person that you see once every couple of years, where you can really talk to somebody who understands what you're doing, or you can try to understand what they're doing. Either way, it'll be good. Talk about physics, grab a coffee. It may not be as good as the coffee in La Baraka. Talk about the Euros, but for goodness sake, just get together and talk. GatherTown will enable you to talk with just 1 or 2 other people just by walking up to them. You don't have to talk to the whole room. So with that, I think that's all of the housekeeping I wanted to cover. I'm now going to ask Gert to welcome us on behalf of ECT Star.
Thanks, Simon, for this good introduction. So I'm just going to say a few words to welcome you to ECT Star. So there will be coffee in GatherTown, but it won't be ours indeed. So I know most of you are familiar with ECT Star. For those people who are not, I'm going to say just a few lines of what it is. So ECT Star was established in 1993, so it's been around for quite some time. It's part of the NUPEC, the Nuclear Physics European Collaboration Committee. And it's very much a community-driven, bottom-up center. And the goals of the center is to do research in theoretical nuclear physics, promote context between theory and experiment, and also to related areas of research. And then finally, train young researchers. And there are typically 2 activities per year that are specific for the training of younger people. The activities of 2021 are here on this poster. It's bigger on the website, so you can find the same poster on the website. As we know, all activities are online, actually till the end of September, and we're currently working on a hybrid meeting starting at the end of September for the 4 final meetings of the year. And hybrid will mean that there will be limited number of people allowed in the villa, and the other people will join from Zoom, via Zoom. So that's quite exciting. And then the training program for this year is 2 schools. The doctoral training program is currently on the way. We're in the 2nd week now. And the talent school will start at the end of, a little bit later this month in July on machine learning. And finally, there's a visitor program, which was not used very much in recent years. So we'll resume this once the whole COVID business is over. So if you're interested to just spend some time at ECT Star for some peace and quiet, then you can apply to this visiting program. We have a Twitter account. We only joined recently in April, so please follow us and you can hear updates and you can tweet about this this workshop, for instance. The address is very obvious to figure out. A few words about related areas, because this is quite important. The core is nuclear physics, as we know, but related areas are very broad. So astrophysics, cosmology, particle physics, quantum matter physics, many body theory, cold atomic gases, also quantum technology, quantum computing, machine learning. And there's a lot of attention to these areas lately, especially, say, to quantum technology. So there is a lot of overlap between this area and general the quantum many-body problem. So this is something to keep an eye on. There might be a lot of interesting opportunities there. This is the scientific board. So the program at ECT STAR is determined by the scientific board via a selection every year. As an example of being bottom-up, the membership of the board is suggested by the associates. And the associates are everyone who participates in a workshop. So everybody who's currently in this workshop will become an ECT STAR associates and can make suggestions for board members. This slide is actually one name outdated, so there's a relatively quick, even though everybody serves for 3 years, there's a turnaround for every board meeting, essentially. But these people have been working very hard during the past 2 years, basically during the whole COVID experience. A few words about funding, because it's very important. So locally, ECT STAR is supported by the Bruno Kessler Foundation, which is based in Trento. And then there is institutional support from the national funding agencies. And in addition, there is Horizon 2020 or EU funding. And what's important here is that ECT STAR is actually recognized as a transnational access facility by NUPEC. And all the other facilities of this type are experimental labs. ECT STAR is the only theory lab, so to speak. So it's quite a special status in this area, which is of course extremely important. Here are some logos of the funding agencies. So the ones on the left are the national agencies from the various countries. So UKRI in the UK, for instance. And then on the right there is some Horizon 2020 funding and some further German contributors. And of course we are extremely grateful to all these agencies that contribute. And that's really it. So for those of you who haven't been to Trento, if you would be there, then you would see this villa and have coffee in the courtyard here. And obviously, we're all looking forward to be together here again in the future. But for now, just I would say enjoy the meeting.
Thank you, Gert. Thank you. And now I'd like to get underway. I'd like to invite our first speaker, Sandro Sorella, who's going to tell us about universal critical behavior in Hubbard models with Dirac dispersion.
Let me share the screen. PowerPoint. Yeah. Okay, thank you very much for giving me this opportunity. For me, it's a great honor to open this very interesting workshop. And I would like to thank the organizer to give me this opportunity to discuss about, to give somehow an overview of several years of research on these Hubbard models and with Dirac dispersion. So this work is basically a collaboration with CISA and the Riken Institute in Japan. As you see, the main computer, the great K computer, is behind me and Seiji Yunoki. Seiji Yunoki is the boss of the Riken Institute of the K computer as far as condensed matter division is concerned. But the main driving force of this work has been one postdoc of Riken, that is Yoshi Otsuda, very careful and did most of the calculation with these big computers. So let me see how the story started in the long time ago. So I was very young at that time, and we discovered with Aereo very nice, at least in condensed matter was not known so far, that a model Hubbard-like as a metal insulator transition and the finite critical value of the Hubbard interaction. We are talking always about Hubbard models. I hope I don't need the introduction of this model. And this is, we were very happy of this work. This probably is one of the main papers in my career. The real story started in a different way. Basically, long time ago, I was in Bella Vista, beginning, was a researcher, young researcher, and then I met Rio Tosatti, and I said, look, I have a very nice model. I have done an Hartree-Fock calculation, and I found a metal insulator transition, but I cannot believe it should be not continuous because the Landau theory has a third order term. This is a Landau dogma. I cannot publish this work. It's too dangerous. Well, in order to understand this, it took much time, but basically, if you do the Hartree-Fock, it's very simple. You have that the critical U, that you need the finite critical U to satisfy the self-consistent equation, because essentially in the honeycomb lattice that we are talking about, the density of states vanishes linearly at zero energy, close to the Dirac cones, and therefore you need a critical value to have a non-zero magnetic moment. So if you expand around the critical value, you find that the right-hand side is linear bidimensional analysis, if you do the integral, basically. And the left-hand side is linear in the difference between U and UC. And so you have, against Landau theory, that where the other parameter should be like the square root of U minus UC is linear. So this can be explained only if you have in the Landau free energy a cubic term, and with this cubic term is known that if you add the fluctuation of the field, so spice dependence fluctuations, then this theory is unstable and you get the first order transition. Well, after that, basically I said, well, I don't understand anything about this theory, but the only interesting thing is that this model is very nice because it's bipartite. I can do the simulation, I go back in my room, I will do the code. And this is the real beginning of the story. After that, basically, you can see the Landau dogma behind that also in what we wrote. The two transitions seems to occur at exactly the same U, and they look fairly continuous. We don't know to violate. Whether or not there is critical behavior, we don't know, but I think this model is nice, and we published. So this is the story, and fortunately, after several years of research, there were many progress, and we know now that the transition is really continuous, despite the existence of the cubic term in the Landau theory, and there is no intermediate region between the two. Also, we know what kind of criticality, because thanks to one of our organizers, it was conjectured that this phase transition can be explained with a low energy model known in quantum field theory, that is the Gross-Neveu, well known in quantum field theory, that is the Gross-Neveu model. And basically all the critical behavior can be explained with this model. The point is that, the main, what we have understood is that you cannot apply Landau theory when you have that fermions have gapless excitation. If, according to Landau theory, you can, in principle, you can integrate out degrees of freedom and you remain only with the theory depending only on the other parameter fluctuation, but you cannot do if the underlying fermions are gapless, and they participate to the transition and change the nature of the transition in a non-trivial way. So this is interesting because this is the theory of relativistic fermions in 2 + 1 dimension that is not only interesting in condensed matter physics to explain this metal insulator transition, but as also introduced in the workshop, has also a much interdisciplinary interest. So the outline of the talk is to show that indeed at the present stage we are able to show with the numerical state-of-the-art numerical simulation that this critical universal critical behavior is indeed true, and basically we have shown by considering a different model. For instance, honeycomb lattice, which was the first model. Then you consider another lattice model on the square lattice with the pi flux to have the Dirac cones, and you get the same critical behavior. Recently, we went also on another completely different model in which we put Dirac cones in the square lattice by adding a D-wave order parameter to the model. This is also interesting because is related somehow to the physics of cuprate superconductors. You want to see how the superconductivity interplays with the antiferromagnetism. In this model, you have a transition between the superconductors and an antiferromagnet, exactly as the cuprate, even though probably the critical behavior has nothing to do, but it's interesting to study this model. And then we completely change the universality class because we studied a negative view Hubbard model on a frustrated lattice that has a different order parameter. Superconductor is 2 components, so there is a U1 symmetry and not an SU2 symmetry. So why, first of all, the motivation to go away from the, say, the unphysical density of states of the square lattice Hadal filling. If you consider the Hubbard model on the square lattice, what you find that the Fermi surface is completely nested at Hadal filling. So the wave vector pi, the antiferromagnetic wave vector pi, connects a large portion of the Fermi, almost all the Fermi surface point, and so the susceptibility diverge at this antiferromagnetic wave vector, which implies that you can have antiferromagnetic correlation, antiferromagnetic order as soon as you increase U. And the transition is trivial due to this infinite density of states at the Fermi energy. Instead, the honeycomb lattice is again a bipartite. You can see that you can divide the lattice in 2 sublattices, black and white. The unit cell contains two sides. These are the elementary vectors of the lattice. And if you you calculate the band dispersion, you find that there are 2 beautiful Dirac cones instead of square Fermi surface. This implies, as we have seen, that the density of states goes to 0 at 0 energy, and we can have a finite critical U for the transition. The effective theory I have to emphasize was conjectured several years ago by Igor Herbut, and the critical point was predicted to be the universality class of the Gross-Neveu model. The first proof of the universality was given by Parker, Assad, and Igor. They put together their data from 6 by 6 to 12 by 18 by 18. And if there is a criticality and you study the order parameter for U larger than UC, all the data should collapse. There are 2 parameters, the linear size of the system and the value of U. This function collapses in a universal function depending only on 1 parameter with appropriate scaling form. And you can see that this kind of universality is very well verified close to the transition. The main point is that what we have understood, that the universality, the gross, you can map all these lattice model that contains Dirac cone in an appropriate Gross-Neveu model with a given number of fermion fields, gapless fermion fields. In that particular case, and you have to count, well, you have to use a convention to count this number of fields. So if you count all, basically, you have, as we have seen, we have two Dirac cones in the brilliance n, but there are 2 sites per unit cell, so you have to multiply by 2 by 2, and then there is the spin degeneracy 2 by 2 by 2, you get 8 interacting gapless Dirac fermions in this model. And of course, the criticality depends crucially on this number. So if you consider spinless fermion, you change the number of Dirac fermions and you change criticality. In this talk, I will consider only 8 components. So for instance, and this known, so spinful model, basically. And if we can identify 3 universality classes. That depends then only on the symmetry that is broken when you are in the insulated phase. For instance, in the honeycomb lattice, when you increase U, you break the SU2, the spin symmetry, by having a finite antiferromagnetic order parameter. So this is told to be of the chiral Heisenberg class, this universality class. Instead, you can have, as I told you, as I anticipated, a transition. If you put enough negative U, the semi-metal is stable for U different from 0 if it is small. And a critical U, you will have a superconducting correlation that break the U1 symmetry, and this is another class, other critical behavior with different critical exponent. And the simplest one is the chiralizing class when the order parameter is discrete, like the CDW transition, and this is also another class. These are the 3 possibilities so far established. Let me discuss about the equivalence of these 2 models as far as the universality class is concerned, and this work was published several years ago. So these are, you see the lattice is completely different. You go from the honeycomb lattice to the square lattice, but the qualitative feature of the spectrum remain the same. You have 2 nodes for given band for given spin. So at the end, you have n equal 8 in both cases. And they should belong, therefore, to the same universality class because both models for large U show antiferromagnetic order. Again, in order to characterize the critical behavior, one study the universal, try to do the collapse fit. So basically the order parameter as a function of U, the distance from the critical point, and the linear size of the system is a universal function of U times L to the 1 over nu. Nu is the exponent of the correlation length. The correlation length has to diverge at the critical point with a given exponent nu. And this beta is the exponent that characterized how the order parameter vanish close to the critical point. The point is that these fit are non-linear and also are affected by next leading correction to scaling that are very difficult. So the possibility, either you do a very large size so that these next leading correction are negligible, or you accept to do non-linear fit, or you accept to do some approximation. This is what we can do with finite size calculation. We cannot do on this fermionic system 10,000 sites routinely, at least so far, like in bosonic model. And then what we have done, essentially, do Monte Carlo calculation of the order parameter and the size. In quantum Monte Carlo, the only thing that you need to know, you compute a quantity with a given error bar, but with the same measurement, you can think to generate fictitious measurement compatible with the error bar that you have. But then you can replicate the data several times, and you can try to do the same nonlinear fit several times and try to understand what is the sensitivity of the critical U, the correlation length exponent, and the order parameter exponent that you predict with the data that you have. And this is what you get from the calculation for the two different models, the honeycomb and the pi flux. You see that basically this is a reasonable way to estimate the error bar of the fit, of the nonlinear fit. Remember, this is a nonlinear fit, so in principle, it may also depend on the initial condition, so you have to check, but basically, we consider this as an error of our fit. And you can estimate the error bar of your fit in this straightforward way. After that, you can realize that the exponent nu and uc, though they are correlated with the critical value of u, they are consistent for both models, even though for the pi flux model, you get a little higher error bar if you want. The fact that we believe to this fit is that if you do the histogram of this value of UC, or for instance, you get perfect Gaussian, so you can rely that the error bar that you have given is consistent with the Gaussian distribution of the data. This is what we have done basically for each data set. For each data set, we build the collapsed fit starting from 6 by 6 to 36 by 36 for the honeycomb lattice. Here I don't see the right-hand side, but I believe we went to 40 by 40. And you see that magically, though the critical U, that is not the universal quantity, because the models are completely different, the critical exponent are consistent within the error bar. I would say that at that time, probably we didn't consider, I mean, this approach looks sensible, but now we know that the error bar were certainly underestimated. I don't believe that we have such an accuracy at present, as you will show from the next simulation. The next few simulations. I mean, the same thing we can do, for instance, even at that time, we realized that, note that there is an extra critical index to determine that that is important. So basically, tell us what with which power the density matrix decays at the transition. You have on one side an insulator, exponential decay. On the other side, a metal, a Fermi liquid exponent. At the transition, you have an anomalous exponent. In order to compute this exponent, we computed the jump in the momentum distribution, so the Fourier transform of the density matrix. Somehow we applied an equivalence of the Migdal theorem also in this case, and we tried to do the collapse fit. They were not very nice, so we have to fix the critical U and the correlation length from the previous simulation, and we verified that the two critical exponent, anomalous critical exponent, were consistent also for this. But you see that we would have loved to do 10,000 sides, but so far, maybe in the next future, with the GPU accelerator, we can do it. Anyway, at the end of the story, I would like to comment about this critical index. The error bar may be underestimated by a factor of 3 or 4, who knows? We will see in the next work. But essentially, if you do the mean field, as we begin 30 years ago, the way the critical, the magnetization goes to 0 is linear. And you see that it's not very different from 1, this exponent. It's renormalized, but not as in the classical Landau theory of the phi to the 4 theory, that there is a stronger renormalization of this exponent. And also the mean field exponent should be 1, is slightly different of the correlation 1. And this should be 0, according to mean field, is very small, it's 0.2. Anyway, so mean field is almost the original Rosati idea was essentially not only qualitatively correct, but almost close to the real quantitative result. Let me revisit also the to have more feeling on this statement that there is now a well-accepted critical behavior for this kind of transition. We consider another model completely different. Basically, we consider a transition between a D-wave superconductor and an antiferromagnetic insulator. The idea is to put more strong evidence of this universality, and also because I like the original motivation to see something that is similar to what we see experimentally in ITC cuprates. So this is what we have done, basically starting from the kinetic energy in the Hubbard model that contains only the hopping. We had the pairing, an explicit pairing correlation with the x square minus epsilon square symmetry. Immediately, the free electron dispersion change from the square lattice dispersion to a Dirac-like dispersion with 4 nodal points, of course, to the 4 values where both the non-interacting and the pairing dispersion vanish, so plus or minus pi alpha. The fact that this model should remain in the same universality class is highly non-trivial, because here we have not we have only 1 site per unit cell, and nevertheless we have twice the number of Dirac cones. So for this cancellation, basically you have always only the degeneracy of spin, and at the end there are only 8 gapless fermion modes in the underlying Gross-Neveu model. So the model should belong to the same universality class, even for a very non-trivial reason. And then we want to understand what happens when we add the U. So we expect that without that, for U large enough, you get an antiferromagnet. You will see an antiferromagnet also in this case. But the thing that is also nice of this model, that we can tune the anisotropy of the Dirac cone by changing the BCS parameter. For instance, if you take the value equal to the hopping, delta equal 1, you get perfectly isotropic Dirac cones. Whereas if you change, decrease by 2 this BCS coupling, you have a very anisotropic Dirac cones. And one point of the theory is that close to the transition, the theory should be isotropic. You should recover isotropy on the spectrum, and you should have the same universal behavior. So this is rather non-trivial to show. And we have done probably a better job compared to the previous works, because we consider the so-called correlation ratio, not the simple order parameter as a function of URL, but an adimensional quantity, a scale invariant quantity, which is basically given by 1, so a pure number, minus the ratio of the Bragg peak of the structure factor when the order, so k is pi pi in the square lattice, and blows up when you are in the, like the volume, when you are at the antiferromagnetic region. And so this value should be 1 when you are in a magnetic phase. On the other hand, if you are in the semi-metallic case, the structure factor is not much different if you take 2 values, 2k values that are very close. and therefore this should go to 0 in the normal phase. You expect that at the transition you don't get neither 1 nor 0, but you get a universal number that should be like the Binder ratio, that is well known to be very important to determine very accurately the transition point for classical transition. And so by analyzing this quantity, since it is scale invariant, it should have, if you neglect correction to scaling, should be a universal function of the distance from the critical point times the power of L. This means that many data should collapse to the same value if U is exactly 0. So this should not depend, the right-hand side does not depend on L if U equals 0. Unfortunately, what you see is that if you try to do to put all together all the data that we have from 8 by 8 to 40 by 40 for the isotropic case and anisotropic case, you see that the crossing is has a big drift, evident drift, and does not want to behave like perfect scaling. And this is clearly explained, as we know now, in this model, there is a strong correction to scaling. And if it is true, of course, you can explain why there is this behavior. Even though it's clear qualitatively that this kind of analysis makes sense, because if the system is increased, they seem to cross more or less to the same point. So you can take with this analysis under very good control the next leading correction to scaling. And this is seen, for instance, if you try to do the plot of the critical U that you get by finding when they cross two lattice sites, L and R by L, where R is a fixed number. For instance, you compare when they cross the 8 by 8 and the 16 by 16, this value is well determined by our data, and you can see how does it change when you increase the size. You can do the same by scaling two sides that are not exactly a fixed ratio, and you get, fortunately, well, in order to show that we have sites enough to large enough to control the subleading correction to scaling, and we have a rather good estimate of the critical value and the error bar. At the end of the story, however, it turns out that it is much more reliable to do the collapse fit without considering the next leading correction to scale, even though we know that they are very, very, very large. If you put them, the fit becomes rather, I would say, not very robust. You don't get very reliable results. So we prefer to do the fit without considering the correction to scaling, but eliminate it, doing as large sites as we can, starting from the large enough 16 by 16, and try to collapse the data. You see the fit, since we don't put the next leading correction, are not perfect, but you see that it works in the sense that you get a reasonable value of the critical exponent, and also you get the main important effect that even these two modes provide a correlation length exponent compatible with the error bar. If you use the other conventional scaling without considering the next leading correction, you get smaller error bar. So this means probably the error, that's why I believe the error bar were underestimated. So you would predict that these two models are not in the same universality class, but I believe more to the above result, and also probably also the error bar. Maybe we can multiply by 2 or 3. I don't know. We will see in the next works and this is also the exponent of the fermion exponent and the exponent of the density matrix. So we can conclude that also this universality class, this model, even though completely different, provide more or less the same exponent. Probably this table has no meaning. And I mean, it's the same information that I give in these few words. And the interesting thing is that in all models, we have considered now 4 completely different models. Honeycomb model, the pi flux model in the square lattice, the square lattice with the wave and isotropic with anisotropic. And as proposed in this paper, there is almost a universal quantity that is very useful for doing calculation without doing very heavy simulation. The critical value of U divided by a geometric mean of the non-interacting Fermi velocity, we don't have to estimate the true Fermi velocity, is almost a universal number, even though there is no justification for this, but it's always true. So if you don't know a model, probably you apply this simple rule and you find the critical value of U, where this is the volume of the Brillouin zone, and this is the geometric ratio of the Fermi velocity. The essential message is that probably all the data that we have so far in the published work, we have probably underestimated the error bar. A more safe estimate is the one that I propose here. Basically, it's not different. And sorry, this is beta, not mu phi. This beta is 3/4. The correlation length is 1.05 with an error bar of 0.05. And this is the critical exponent of the fermionic field. If you look to the data, they think the numerical simulation by Monte Carlo are in much less disagreement than any result obtained by analytical tools. For instance, you see the large N simulation, if you do the Paderi summation, in the region of interest, that is n equal 8, has a huge indetermination. So at least we can say this is reasonably correct and consistent between several groups. Then let me discuss also a different, so far only one universality class I discussed. So let's change completely the model and consider a frustrated lattice, triangular lattice, to study the so-called chiral XY universality class.
Sandro, you've had 35 minutes now, so you have another 5 plus 5.
Okay, sorry. I was thinking 30. Okay.
Okay.
So let me briefly discuss this. This is the model. You put a flux. This is a square lattice modified in such a, if you add the bond, it is equivalent to the triangular lattice. And you have to put a flux pi to have the same Dirac points. The same Dirac points that we had before. But why we put the model in the triangular lattice? This can be easily understood by doing the strong coupling limit of the model. This is a negative view. So you want to see when it becomes superconductor. Because in the square lattice or in bipartite lattice, there is a competition, I mean, between CDW and superconducting stability. If you have a frustrated lattice, basically, you can map the model, the negative view model, to a positive view by doing a particle law. By doing this, you have a negative sign in the electron spin down particles. And this can be gauged out only in bipartite lattice, so this negative sign cannot be avoided in triangular lattice. And this means that if you do the corresponding model at large coupling, the Heisenberg model, you have frustration in the classical part that corresponds to the CDW order in the physical unit before the particle hole. And instead, you have a ferromagnetic coupling in the XY plane that is perfectly not frustrated, because ferromagnetism, as we know, is not frustrated. So this clearly show an argument why, when you put frustration, you can establish only the BCS order. So you are in a genuine XY chiral universality class. And this is what happens when you do the simulations. Basically, if you increase U and you do a very careful finite size scaling using 2 different sequences of sites, Yoshi was able to get the same result. So these results are very, very well converged. And you see that all of a sudden, between the value 7 and 7.2, you have off-diagonal long-range order in the sense that this anomalous average is different from 0 in the ground state. And you can do the standard plot of the extrapolated to the thermodynamic limit result, and you find the transition is continuous, as we expect. And you do the collapse fit, and you get beautiful collapse fit, and you are able to determine the exponent. You see that now the value of beta is quite larger than 3/4, so it's even more classical, closer to 1. But on the other hand, the correlation length is slightly more different than 1. So it's difficult to have a meaning of this critical index, but an intuitive meaning to this critical index. But it's clear, even if you multiply by 5 this error bar, they are quite different from the previous universality class. This would be 0.75. This is very far from this value. And this is basically, I would skip that again, we have a better way to determine the exponent of the fermion field, and it turns out also this to be slightly different from the chiral Heisenberg universality class. It was larger than 0.2 in this case. But what is interesting to discuss in the last few minutes is a very nice transition that was shown recently by Lin and co-workers by studying a model that has a CDW transition, so a discrete order parameter, and you would expect that you have a chiralizing universality class at the transition. Instead, just because at the transition, the cubic, this dangerous cubic term in the Landau theory, gets irrelevant, you get an emergent SU2 symmetry. So the prediction of these authors is that this critical transition belongs not to the chiral Ising universality class, but the XY universality class. And they predict some exponent with very large error bar, but they are in good agreement with our exponent, and we believe should be more accurate, but certainly different from both the chiral Heisenberg and the chiral Ising universality class. In the chiral Ising, this should be much larger, this exponent, and in the chiral Heisenberg, this should be much smaller. And this is consistent also with their result, basically, outside the error bar. So this is an interesting result that we can have a valence bond instability instead of an antiferromagnetism before the antiferromagnetism. And this is something that is not realized if we put the long-range Coulomb interaction in the model. This is a work, recent work by Assad. If you put the long-range interaction, what happens is that you make the transition qualitatively similar, and the long range has an effect to screen more the short range part, so that you have to increase the value of U before getting the antiferromagnetic Mott insulator. Instead, what happens in the realistic system? I just flash that, well, we studied this with the realistic calculation that we have established with state-of-the-art. These two Borg VB, we are doing a school recently in Trieste to teach this tool. I mean, I spent a sort of years. I hope it is useful also for other people. But we analyze this graphene, the real graphene now, as a function of U over T. How to simulate U over T in the realistic system? We just you can apply negative pressure, so you squeeze, you increase the distance between the carbon bond. Since the U is expected to remain independent from the distance, while the hopping is decayed exponentially, you go in the strong coupling regime when you expect the transition. And instead of finding the antiferromagnetism, we found the Kekule dimerized region. Sorry, I have went out of time, but just flash the conclusion. We have shown that is certainly the case. We have understood all the universality class in a realistic Hubbard-like model, but still probably there is some work to be done to understand the real graphene with Coulomb interaction. Thank you for your attention.
Thank you, Sandro. Thank you. That's a wonderful introduction to both the physics of the Hubbard model, its relation to Gross-Neveu, and also to our workshop. We have time for one or two quick questions. If people would like to either speak out or put something in the chat. Lucas Janssen. Lucas has a question. I'll read it. Lucas, are you there?
Yes, I'm there. I can ask it in person. So the question is, is it possible to simulate at large n the same universality classes with the same accuracy in order to be able to compare with large n predictions?
Good point. Well, so far we are limited to lattice model with to be honest, I don't know if probably Fakir Hassel can answer. It has studied
yeah,
model.
So it's possible to go to larger n, right? In principle, if you can, depending on how you formulate for Monte Carlo, you can go to larger n. The question is, with the same accuracy, Lucas? I think yes. The answer is also yes. I think
yes.
Thomas has that. Thomas
is
around, right? He can answer also. He did some calculations as a function of n.
Actually, way back we did simulations of the Gross-Neveu model with yes, the answer is yes. If you set n very large, you have to invert bigger matrices, but the statistics, the fluctuations are so much smaller that the answer converges, and kind of one plays off against the other.
So if you do that, Simon, if you do that with the BSS, you don't have to invert bigger matrices, because if you explicitly calculate a determinant, n is somehow like for free.
Yes.
So it's basically just an n from the action.
Yes.
The only issue is the trotter error, which grows. Sandra, you have to just be very careful. So you have to scale the trotter as a function of 1 over n, the trotter discretization. Otherwise, you may run into problems. That's the only issue you have. So you pay something for the n. It's not completely free.
Yes, it's not completely free.
But it's pretty free, right?
I would expect, however, that you can do similar size. Yes.
Yes, you can. I'm sure you can.
Michael Sharon has asked a very similar question, so I'm gonna skip that, Michael.
Absolutely, yes. It has been answered on the way.
Are there any further questions?
I can ask another one.
Please.
So when you look at the Kekule transition, so the idea is that the Kekule transition also has a cubic term if you write down a Landau-Ginzburg. So you would also expect a first order transition there, but then you can basically show that the Dirac fermions make it a second order transition. But at the same time, you would expect a subleading exponent which is close to 0. Which would make your scaling analysis quite difficult. So is that something that you see, that in the Kekule case, you're having more trouble to see the scaling?
Yes, I mean, in the Monte Carlo calculation, this was, let's say, at this level, we are at the level of mean field. And basically, we do a little more than mean field because we do a variational, we use a variational wave function with explicit correlation. But I don't know if you can believe to the transition. Anyway, from this wave function, it looks that the transition is continuous instead of being first order, unless it's very weakly first order. So this means that probably also in this case, we have to apply the Gross-Neveu universality class of the Ising universality class. I don't know.
Thank you. I'm going to draw things to a halt there. So can we all thank Sandro again for a really nice talk.